Welcome back. It is it is now another day to work on quantum mechanics. So yesterday, well, basically for the last few days, I've been kind of redoing some questions and going through some concepts that I found a little difficult, that I was struggling with, and trying to master them and trying to get better at them. Now, one of the things I've been saying kind of throughout this project is that this class is harder than I thought it was going to be. And this kind of thing happens when you do learning projects like this, just because there is all projects have this issue where you aren't entirely sure whether you can reach a particular target. I've even written an article about this, about setting goals in the middle, and one of the reasons for that being that you don't really know what is a challenging or easy target. Now, I kind of did that for this class, but for this one here, there's a real obvious outcome, which would be passing the final exam. I mean, it's not the only outcome I could consider. And obviously, if the class had been too easy, I could have considered, pushing on to 805 or 806 or something like that, like with the later classes in quantum mechanics. However, this is still a fairly good benchmark for what you should try to do in this class. And so one of the challenges I just had is that I wasn't quite sure how difficult it was going to be. I knew it was going to be difficult because I don't have all the prerequisites, as I've been saying. And the prerequisites I do have, I haven't done since the MIT challenge, which was about 8 years ago. So that means things like, solving differential equations, taking integrals, even just like simple things like, chain product rule for differentiation. These are things that I needed to remind myself on because I haven't worked with any problems with them recently. And not to mention that this is a difficult class. So one of the things I noticed during the MIT challenge is that sometimes as you get further on in the classes, they get more difficult. It's not always the case. I found that when I did the MIT challenge that I found the computer science classes quite a bit easier than the physics-based classes. I don't know whether that's just me. It could be in relation to the fact that, I have more, even outside of that challenge and outside of those things, I have more experience programming than doing this kind of mathematics. So that could be it. I've talked to other people, and it could also just be an intrinsic difficulty of this system. Just that, a lot of the discrete math arguments, at least at the undergrad level, I think obviously once you get to proving, is P inside NP or those kind of questions, it's a whole different ballgame. But when we're talking about the undergrad level of analyzing algorithms and making software and understanding how a CPU works, there is certainly, it's not an easy challenge either, but in some ways it can often be a little bit easier to calculate than if you're doing kind of difficult calculus problems, particularly because once you get past differentiation, once you get into integration and beyond, there's no guaranteed procedure to solve certain formulas. You just have a bunch of tools and you just have to throw them at the problem. And sometimes the problem will break down if you recognize some kind of pattern or trick, and other times it won't. It'll just be a mess and you can only solve it numerically. And so quantum mechanics is really just further along in that stream for me, and it's more challenging for that reason. So it's been I've been going back and forth on sort of like, what do I think about this and how am I handling it? And basically the decision that I reached is that regardless of whether I feel like I got to the level I would have liked to have reached of, passing, or I would say like clearly unambiguously passing final exam for this class, I do feel like I've learned quite a bit, and I do feel like sticking with this as my kind of end goal is going to cause me to learn more than any other approach. So I don't really feel like, even having gone through this, I don't really feel like I would have done anything differently. I think I might have been a little bit more careful about annotating what I got wrong for questions in the problem set, just because I wasn't anticipating doing this many run-throughs of it. Normally with a problem set, I would only do any given question once, just because, I would have more feedback material than I do actually have questions. So if I were going to do things, I would do new problems. Whereas here, I would have paid a little bit more attention to that. I don't think it's a huge issue. I can look in my notes and see what I got wrong for things, and I can work on those things and stuff. But I don't think I would have done things too much differently. I mean, I could have taken 803. That would have definitely made it easier to do this class. But whether the time spent doing 803 and practicing those problems and finishing that thing would have just added more time for this eventual goal, I don't know whether it would be more efficient for doing this. So definitely, if my goal were, I want this class to be easier, then I would have spread it out over more time. And just, it's just about spending the amount of time. And this also brings me to another thing, which I think is very interesting, is just how when you are in an academic system in a school, they kind of give you a fixed amount of time for doing a particular class. And the understanding is that this is how long the class takes. And I feel like I kind of showed that's not always the case, at least during the MIT challenge, that when you have complete flexibility over the materials, there's a lot of classes you can do much faster than that time period, just because of the background knowledge you have or how you organize your time or various other things. But in particular, for some classes you find easy, you will be able to do the class faster than the 4 months or whatever that it's normally drawn out over. On the reverse, though, it's also true that there are some classes that they will say this will take you X number of hours. And if you don't have the background that they anticipate you to have, or it's more difficult for you, or you need more practice, it might take you longer than that. And so I've kind of talked about this idea of ultra learning, and ultra learning in some ways is kind of synonymous with people who take aggressive sort of self-education projects. But I want to sort of point out this is not the same as just trying to learn something super fast. What I wanted to say the difference is that, I would say a normal way of approaching this is that maybe you'd watch the lectures, maybe you'd watch the lectures and then, okay, that's it, right? Whereas the difference here is that I'm really trying to do the problems. I'm really trying to evaluate myself on this material, which I see as being less common in self-education. Obviously, when you're doing a class and you have to pass a test, you do what you have to do to pass the test. But I think definitely for self-education, it's more common to read and watch instead of actually doing practice. And I don't think that ultra learning is characterized just by doing practice, but I do think that there's what I would characterize the method as is involving a focus on efficiency in learning, even though that often involves doing things that are harder or more uncomfortable or more difficult or more frustrating or, whatever than the sort of normal approach. So that's where I'm at right now. I've got, it's Tuesday today. So I've got the rest of this week, and then I got Monday, Tuesday, next week to work on it. So, 6 days, let's say, in total. And I'm not sure how far I'm going to go. I have a list here, and I'll switch over to this view here. So I have this list of what I would like to, what I'd like to work on. So I had this list of concepts, and you can see I've already crossed out some because I did sort of find techniques for these concepts. There's some that I have not crossed out, but I kind of decided not to do. So even though this isn't all crossed out, geez. Even though this is not crossed out, it is also something that is not necessarily that I've done most of the things on here, or I've done most of them. The facts and flashcards, I'm not entirely happy with how I did that. Not because I think that there's a real better way of doing it, but this is a class that that is sort of on the edge of, is it worthwhile to do? I do think memorizing some of these ideas is important, because there were concepts I was forgetting when it came to doing the problems on the problem set that was not on a formula sheet. So like, recall this, and then it's some formula. There's two things else about that, though, I would say. One is that if the problem set does not give a lot of information, because the assumption is that the student can just look it up. So there's a kind of, because it's open book, anything's fair game. And so they'll often include things that are not on the formula sheet, but that would probably be on a formula sheet if it were in a final exam. So I have to keep in mind that. And I also have to keep in mind that, a lot of these ideas, it's probably better to work with them rather than memorize them. So I'm kind of going back and forth on this. I have made some flashcards. I might make some more, but we'll just see about that. And the concept end, the only thing that I really had left to do that I really wanted to focus on was this crystal momentum. I have a couple other ones I have here. Oh, I put this one new, setting up and solving differential equations, just because there's been a couple questions that have been differential equations, and it's the process of setting up the equation. I feel like I kind of know how to solve it once it's on the page, but it's kind of, okay, we've got this, and this is changing in time. And you know what, I remember doing it, but I'm not well practiced in it. And then at the top here, I have all these questions that I wanted to revisit from the problem set. You can see I crossed off these ones. 2 of them I had not done before, and 2 of them I had done before, and I went through them. And this 1.1 it's the first question in the problem set, and this is one of the hardest ones that I had to do because it's all old physics. It's all physics from electromagnetism. It's not any new stuff, but it's also challenging because it's differential equations and things like that. So it's not an easy problem in those things. It's not just, plug a few things into an equation and solve it. You have to actually work around with it and make some assumptions and that kind of thing. So I did put a little note here to go over that conceptual piece. So there's some other questions I wanted to do in each of the problem sets. This is not a full coverage. Obviously, you can see like I'm missing 2.2, 2.3, but I put this way just because these were the problems that I think I not only got wrong, but would benefit from a second attempt, would benefit from it being exposed to the problem fresh, trying to recall how it works, trying to recall the principles involved. So I'm going to work on these problems today. I was going to go back and forth between doing this kind of work and that kind of work, but there seems to be a lot more of this than this. So I think I'm going to just focus on these problems right now. And once this builds up a little bit more, once I have like another, several concepts that I want to go through, I might take a little break. Or if I'm getting kind of exhausted from this, I might switch over just because this tends to be a little bit easier mentally than this. So, sometimes it's good to balance it if you're feeling tired. So what I'm going to do right now is, I've got these flashcards. I might as well just go through and do a quick set of the flashcards. I don't have very many, so let's see if I can remember them. So here's my flashcards. Hopefully you can see it here. So first flashcard, what is G naught? Well, G naught is the dimensionless strength of the well or barrier. It's used in any kind of scattering problem. And I believe the close form of it is square root all over mass, length, and potential are all in the numerator. And then in the denominator, I think it's just h bar. Maybe there's a 2 up there. So I would go square root 2mv L over h bar. Oh, so the L is outside of the square root. Okay. All right. So the LZ operator applied to the spherical harmonic while M, I think, just gives M while M. So because this is the amount of definite angular momentum in that direction. Oh, h bar M. Can't forget units. L squared, this is L times L plus 1. Also h bar squared this time. Won't forget my h bars. There we go. LZ in spherical coordinates. That is, I want to say, I h bar d phi. Negative I h bar d phi. Okay. What is the wavelength of a particle in terms of h bar, m, and v? So mv is the momentum, which is p. So length is equal to, so we have lambda, this is equal to h over p. So that would be h bar times 2 pi over mv. Yeah. Units of h bar is kilograms meters squared divided by second. Yeah. Express the energy operator in terms of the A. Well, I've got it here. I got to cover it up. A plus. So it's A plus, A minus, plus 1/2, and all of that is times H bar omega. Yeah. And the units of this is 1 over root L, or root meters, I guess. Yeah. Okay. So did a few flashcards. Flashcards are good like that. I think, you know, I might make some more. I might make some for some trig identities. I might make some for a few situations here. But yeah, there was a couple other ones that I wanted to put in. The problem is that I got a lot on these formula sheets, so I'm going to have that when I'm doing the exam. So I don't know whether it's that necessary that much. Like I was going to put for A, but then that was also on the formula sheet, and you know, I don't think that like knowing the spherical L squared and spherical coordinates is going to be all that valuable, just because it's going to be it's so involved and stuff that I don't think that they're going to make you memorize that. All right, so oh yeah, integrals of Gaussians is probably a good one to do, because that one you could do by hand, but it's better to have it memorized, I think. All right, so I'm going to put this over here, and I'm just going to go through now problem set 2. So let's go 2.1. And let me just switch over here so you guys can see. Oh. So, all right. Let's do problem set 2. So 2.1. Okay, this question. This was the phase and group velocity. Let's see if I remember this now. All right, what is the difference between phase and group velocity? How do they differ in ocean waves? So 2.1a, phase velocity equals speed of individual harmonic waves, and group velocity equals speed of wave envelope or packet. Okay, that's just a definition. How do they differ in gravity waves in the open ocean? I don't remember what the dispersal relation is for gravity waves. Let me just look. Do we have the WK? So gravity waves are omega naught squared is equal to GK hyperbolic tan HK H. What is this H? Oh, this is the height. Is it the height? and water depth H. I'm going to say just this is KH. So, how do these differ? Well, we have phase velocity is equals this is square root of jk hyperbolic tan kh. Oh, I forgot to do the hyperbolic. I'll put this up here. That was one of the things I was going to do. Hyperbolic. Okay. And then the group velocity is this, which is equal to what? Let's just try to do this real quick. So we're going to have 2 d omega is equal to do I want to try to do this one? Let's just try to do it, and then we'll see how it goes. All right, this is going to be g dk Wait, it's not 2. How do I do it when it's just partial differentials? Because we're going to do dw. kdw. kh, where's kh? And then we have what's the derivative of hyperbolic tan? Let's just look that up. Where are they? 1 minus tan squared h. So tan h squared. Am I forgetting something in the center? Quotient rule. I think it would come out here. I think it would come out here, right? K squared h. Equal to this is just an awful differential equation. I don't think I'm going to try to solve that here. How do they differ in gravity waves in the open ocean? What is our phase velocity? So square root of this mess. I think hyperbolic tan is this function. So it should be like kind of like this. A little bit like that, right? And then the question is, I don't know whether we can do this dwdk because I don't know whether there's a actual maximum for this. I think we can say that the group velocity it's going to be lower. I think group is going to be less than phase. You might guess. This is B, not BB. This is still A. I think that's it. And then let's go to formula sheet over here. Now we got B. Why do waves break on a beach? I think, if I remember correctly from the last time, that the I think it's that the waves we've got so as this is going down, it's getting smaller and smaller. That would be pulling us this way, which means that it means that the I think that's right. So as h decreases, it's kind of going downwards, so it's slowing down, and then that's causing it to pile up. And then that's why they break at some point. That differential equation will break down. And then C, a surfer is waiting for a wave packet of ocean waves approaching a beach. It's accurate or illusion. So this is accurate, and it's because why big waves tend to approach the beach in sets. So you have some kind of wave packet like this, which has some kind of, and these little guys are moving faster than the big guy. Group slower. So these things are going down as they get closer to approaching it, so that they seem to disappear while this surge tends to happen. So that's why they'll approach in sets. All right, let's see what the solution is. So hold on a sec. I put this as, yeah. So phase velocity is W over K. This is dk, yeah. Yeah, this is square root right here. Oh, okay, here we go. We have okay. So we have this gk divided by k is equal to root g over k, and then our d. So 1/2 speed. So this was right, but I didn't get the exact number. Okay, this is right. Scrunching up. And okay, yeah. All right. Feel good about that one. Let's go on to 2.4. Oh, I didn't do 2.4. So this is a new problem. Didn't do this one? No. Oh, email. I have a cat visitor right now. All right. Did I not do this one? Did I not do this one? I have it circled that I didn't do it, but is he disrupting the camera here? Okay, I think it's good. I have to be very careful. I've got this desk camera, which you can see in here on the camera, and I have a cat right here off screen who wants to sit next to me. All right, 2.4. In 804 conventions, a function f and its Fourier transform. I can't believe I didn't do this one. All right. Well, I'll do it again anyways, even if I did do it. Okay, so basically we want to show A. We want to show that our okay, there you go. here. dk squared h bar k. All right. I'm assuming this is from negative infinity to positive infinity. Let's see. So let's take Fourier transform right now of our function. So if we take of this is our Fourier transform e to the I k x f k 1 over root 2 pi. And we know that so this is fact number 1. And fact number 2 is our momentum operator is going to be the x I star x minus I h bar d dx psi x. All right, so we need to combine these two facts. So I think, what if we take all of these as Fourier transforms, I'm just going to flip this guy over here. This is visible. Let me just move this. I'm always a little bit nervous that my camera isn't showing things. So if we put this into this one, what do we have? So let's take the Fourier transform of each of these guys. So and then let's put the and there would have been 1 over root 2 pi, but we're multiplying by twice, so we can just go 1 over 2 pi. And then we've got I h bar. I'll put the k here. Oh, I should put my e to the I k x. Hold on a second. E to the I k x. This is e to the I k x psi k. So we have 1 over 2 pi. Can we swap the order of integration here? Because these are both over the same term, let's just, I think we can just merge the integrands, can't we? It's a linear, if we have f times g this, does this go to, I don't believe so. Hi, Yang. So I can bring this in. So I'll just do that first. So I've got dk. Hello, cat. There you go. Push your tail over. There we go. I got I h bar. And then let's bring the ddx on this. It's going to be so ddx of this thing is going to be ik e to the ikx psi k plus e to the ikx psi prime of k, right? I'm not sure if I'm making this the right approach. Let's try doing it this way first. So we have can I just swap these? Change the order of integration. Like, can I go dk dx So this is going to be minus minus h bar k okay. If that were true, so I'm going to put this. I don't know whether I can do that. I don't think in general you can do that because the order of operation is going to matter here. But yeah, I feel like I'm doing some shady stuff here with these integrals that I should be doing. Oops. Ooh. Well, let's work with this, me not doing this properly, and then just sort of see where we go. H bar k over here. I guess I can't put the. Let's not put up there. Just put 1 right now. And take the minus sign up, -1. And then we have dx e to the I kx psi. Thanks, Bjark. Scooch cat. There you go. Well, this isn't really giving me what I wanted. All right, let's start fresh. So I think if we look at it, we need to get the function in terms of the Fourier transform of our wave function. So I think you could just apply this to each part of this and then go through, which is kind of what we were working on. Apply this to this. And then you're going to get the IK out. I think I forgot the minus here. No, I'm doing the inverse, so I'm doing this one here. what if instead of working with these, we just did it as terms of operators? So we had we have this. So we have this, and then now we want to do let's just say Fourier this. Does the Fourier transform commute with? So let's go. Okay, and then we want that's not going to help. We have to have this derivative on the outside here. I mean, the Fourier transform's got to commute with this. This is why we can swap it around. Because we could just easily boot this. So the right word for negative h bar k e to the ikx. Oh, wait. This is k. This derivative of this k is not a function of x, so we don't have to do that. So we just have this down here. Oh, okay, that makes things a lot easier. I forgot that this is k. All right. We can have equals 1, 2 pi. How do I switch the order of integration here? DDF and DDX should commute, right? Let's just say for a second, then I can do this. Put a big question mark here because I'm doing 2 steps and I'm not sure whether I can do. But if I could do this, we then recognize that now these guys are gone because we're now integrating over x and these are k. So I can just move these 3 out. And this e to the ikx is going to cancel the pi's when I get there. And then it would be so that is based on the idea that I can swap that order of integration and merge it. How can I justify that? So integration with respect to x and integration with respect to k, do those commute? Um, this is the key question. So this is I, X, I, K. K, F of, doesn't matter, I guess. I think this is 0. I think. All right. So B would be this just squared. So we can follow the same logic from last time, except now we've got dx. Yeah, dx. All right, K. UDI kx. Well, this time we're going to do I h bar squared so this is going to bring this down twice. So we have this is now h bar k squared. So this the same logic is going to get us the same answer. And and we should have that. Now, some arbitrary function f. Expectation of f of p. Now we have f of p. We have to do it like this. Minus IH bar. Minus here. I say h bar d dx e di ax psi k. And so this right here is going to be our f h bar k. So this is going to become this. And I think this is because on x that we can do that. So this would be how to solve it. I think it just depends on some assumptions about how we can handle these operators that I'm not as confident in. So let's just look at the answers now. And okay, let's look at this. All right. Okay, I proceeded here. Oh, interesting. So what they did, so I'm going to write this on the page. That's clever. Okay. To conjugate e to the I kx. on down. Hey, come on. All right, and then they had K e to the I Q X H bar D dx e to the I K X. And then this is just our H bar K come down. Yeah, I don't think I did do this one. So now we have Fubini's theorem. Let me look at that off of that. All right. We have equals e to the minus I Q X. I'll do this I K minus Q X dx Q dk. And then this is going to be equal to 2 pi delta K minus Q So we have psi k minus q q to k So if we do the, so I think I will circle this one here, because that's going to be important too. Well, this was actually more involved than I was expecting it to be. This was really clever of using the two variables. I forgot to conjugate that, which was silly. And this delta function, I think, is so if we have f times d of x, what do we get? Gets f of zero. We have to get f of this is just the yeah, I think we just get f of 0 right here. So if we have d of f is q, this should just give us f of q by the definition of the delta function. Okay. So I'll cross this out, but this one was interesting. All right. Let's go over to 2.5b. Oh, this is more integration work for delta functions, so let's go. So let's go negative infinity d of x, and we'll put this x dx f of x. So we want to show this is equal to 0. So if we integrate this, I think this is going to be, we can just change the order here. Dx. And so this is just going to be x f of x. Evaluated at 0, which is just 0, because it's 0 times whatever the function is. 2 dx equals dx. Okay. I should put this here. So let's just do this side here. This is going to be f of 0, and this is also going to be f of 0. So that's also true. 3, this is harder to show. I think the idea here is that by making this c of x, we've taken our infinitely small mass and made it even sharper and even taller, right? Hmm. What if we turn this to some kind of, so we want, so if we represent it in terms of limits, so this is equal to this is equal to Can I express this in terms of limits? Essentially, we have some kind of square here, and we want as so our delta function could be seen as zero at so like this. Right, we could use as this function. And then if that were true, what would we do? We go negative infinity, positive infinity. So I think we can just change this to minus epsilon dx of I don't know how to do this with the definition that they've given me. This is just going to give cx. This is not. Let's look at the definitions again. Oh, right. Okay, hold on a sec. Yeah, we have to do substitution of variables here. So let's try it that way. If A and B. And then our so let U equal cx du divided by c. Where do we get the? Why is it magnitude? got du divided by c. Y is the absolute magnitude. Oh, because it would reverse the orders here. So this is divided by c divided by c. So if this were negative, it would flip the orders, and then you would get if c equals negative c, we get order flips and okay, so this one is this way. All right, this one now. Oh. What is x? X times b. So because of the last inequality, we can go this, this. All right, and then so this will evaluate to x plus, so at x equals a, x equals b. How do I show that? So this part only has contribution at x equals a, and this part only at x equals b. So this will evaluate to okay, like that. And then let's go v. F of x delta x minus a equal to f of a delta x minus a. Yeah, let's do this. Negative a dx fx. Now we want to get this in this form, so we do dA S and A. So let's go substitute this one with a minus, and we get dA of f of a delta a minus x, and then swap, and it matches this one. So that's how you do that. All right. I don't even know whether I need to check those. I think those are good. Let's just look at them anyways. 5.2.5b. Okay, I feel pretty good about those. Oh, I was wrong. There's one more question from 2. wanted to do 2.7. Let's go 2.7. Why the wave function should be continuous. All right, okay. Consider the wave function from problem 6, which is just a step function centered at the origin. So for n so we've got this right here. And the first question is n what we have to have? This has to be equal to 1. So this becomes, this is just equal to itself. So it's going to be equal to, and we can just change these to negative a half, n squared, right? N squared x at negative a. One over root a should be our n. So I've done that right. This is going to be minus, so we just cancel that. All right, and let's do 2. Well, I don't know. Calculus is one aspect of math. So Matan says it seems like math only really starts once you get calculus. Calculus is just one aspect of math. So when I did, as I said, doing the MIT challenge, there was a lot more discrete math, which for me, I found a bit easier. Very different kinds of problems. Not always easier, but just for me, it was a bit easier. Calculus, a lot of it is the fact that you have to know the rules really precisely, what you can and can't do. And I'm a little bit forgetful of that. So for instance, in the question we were doing here, I knew I couldn't do what I wanted to do, but I didn't think to do what they did, and it was tricky. But it's kind of like you kind of know what the right answer is or what it should be, but sometimes just getting the math to work out can be tricky. So now we're trying to figure out uncertainty in x. So delta x is going to be equal to the square root of x squared. Oh, thanks, Rasmus. All right, now we want to calculate this uncertainty. So well, we have to basically take, so x squared is going to be equal to negative positive infinity. And these psi is purely real, so we don't have to take the conjugate. X squared psi x dx. And we can just do this again. And we have 1 over a squared dx is equal to I just want to do it in one go. I'm going to go x squared is going to be 3 1/3. No. Yeah, 1/3 x cubed times 1 over a evaluated at minus a halves. And then we're going to have this minus 1/3. Put a little minus there. Cubed 1 over a. All right, so let's try this again. 1/3 a cubed over 8 times 1 over a. So we can just get this to be squared. And then this is going to be plus, because we're going to have the minus sign cubed is going to come out. And we're going to get 1/3 over a squared. Again, over 8. 3 times 8 is 24. So we have 1/12 a squared. And then our expectation in x is going to be 0. This should be equal to 0 because it's symmetric. So this is going to be delta x is going to be equal to 1 over root 12 a. That should be right. I don't know what I calculated for the last. All right. And let's move on to B before I check those answers. So B, calculate expectation value momentum and momentum squared using the Fourier transform we calculated in problem 6 and the result from problem 4. I didn't do those this time. I think it's going to be divergent, but I don't have the results for that one. Maybe I'll just do this A. We'll just sort of see how it goes. This is 2.7. Oh, I can use this here. Uh, so let me put this over here. So expectation value of P is going to be I don't think this is purely real. So again, we can do dk. I'll just do hk. K squared this is also symmetric. Here we go. So we want to just do, let's just do squared. Yeah, because the K would be canceled here. So this is going to cancel, we're going to get a K, and then it's going to be doesn't converge. All right, let's just look at this here now. All right, which is correct. 1 over root A, and this one is 1/12, which is root 3. Yeah. Where's the K? Oh, right, oh, right. I had 2 of them here. Okay, so I didn't do quite the right math there, but it's the same answer. All right, we've done 2.7 now. Yeah, it's still pretty early. Don't need to take a break yet. So 3. 3.2. We want to do C, F, and H. 3.2. C is going to be show T hat L is equal to E to the minus L D hat. All right, so E to the minus L D hat is going to be equal to, all right, how do we Taylor expand again? Taylor expansion is, let me just remind myself Taylor expansion from now. So we have some polynomial A0 x 0. Let's put AX. This is the Taylor series. So we've got some polynomial, and our AIs is equal to f of I right? So for e to the x, this would be one plus let me just do this. Yeah. All right. Now, what is our how do I get this to show that this is the translation operator? All right. Hmm. So let's just try it with arbitrary x. So we have e to the minus L d f of x. And on the left-hand side, we have TL of f of x. So I want to show. Can I try inverting it? Like if we do ELD f x minus L, this should give us our f of x, right? And that would show this equality. This is wrong. This should be f. No, I think this is right. No, you know what I have to do? I have to Taylor expand the f of x minus L. So f of x minus L, 1 So let's just do it with u first. 1 f think I'm missing one here. Because this should be f of what was our Taylor series again? It was, if we had it shifted, it was equals to f of all right, I'm gonna look it up. Forget how to do the Taylor series here. Taylor series. Oh, let me just, I had the link. There we go. Here we go. So it is f of x is equal to a plus x minus f double prime x squared dot. Okay. And so I definitely did this wrong. So this is f of 0 prime of 0. Let's not have the, do I have the x minus L now? Yeah, let's do it here. This is going to be let me just try it with the 0. So we have f of x is equal to f of x minus L. That's the right way to do that. Right, okay. So it's f of 0 plus f prime of 0 times x minus L. It's f double prime. Back to here. F double prime of 0 x plus area plus dot dot dot. So this it's because this is minus L because we have these are the coefficients to a polynomial, and if we are doing it for f of x, it would be x, but we're doing x minus L, so this is this. And then we have our e to the minus L d hat f of x is going to be equal to f of f of x plus let's not do it like this. Let's do it with two Taylor series approximations. So it's e to the L times f of 0. If I do 2, it's going to be too many. How do I show these two things are equivalent? I guess I can do this. Is that valid? Not really. Like this thing here is a polynomial. It doesn't have any x's. This thing here is a polynomial. So this is That's equal to this. This thing isn't. Taylor expand this. So if we take f of x, it's going to be equal to f of 0, f prime of 0 plus f double prime of 0 So we Taylor expand this. This is x squared, this is x cubed, dot, dot, dot. So if we were to translate this, okay. And if we were to do so this is I had minus. I better show this as equivalent. I can't just show that it undoes the other one. What if we were to divide out all these terms? Like this is going to be 0 though. It's going to be minus L, right? At a What else can I do to make this work? Wait a minute, let's try something here. E to the This is minus LD. Well, let's take f of x. It goes to f of x minus 3, or x minus L. So if we take x, we have f of x minus L over this should be so f of x ooh. So if we divide these out, what do we get? We get, well, this becomes 1. This becomes, let's not divide them. Yeah, we have to divide them. And this becomes minus L divided by x. This becomes x minus L squared by x squared. Becomes x minus 3 cubed divided by x cubed. So this becomes 1. This cancels and we get damn, I'm not going to have the ddx there. I think I'm stuck. All right, let's check the answer here. This was 3C. Oh, 2c. Okay. All right. How did they do this? Let's see if I can pay attention this time. All right. Squared over dx squared plus dot, 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 and then okay. So we're going to get on even minus OB on F. All right, this is what I had from before. F of x is L prime of x L squared F double prime of x plus dot dot dot. So I think my mistake here was because I had, what did I have? I had f of, I had f of x minus L equal to f of 0 plus So I think this is just a different way of doing the Taylor series, Taylor expansion, than I had learned. Well, that's a little frustrating. Yeah. Because I learned this form, and they have this form, which obviously makes it a lot easier. Oh boy. All right. Let's do F now. Where am I here? F. Part C and E to determine how D acts on F of K. Does this make sense? Oh, hold on one second. Back on. So maybe I will put this as a little fact. Okay. How does D act on F? Okay. So here we have the dx of this is let me just remind myself Fourier transform going from, so we want d of x e to the I. So we're applying this on this. Should just be able to move this guy in. This guy should just cancel, shouldn't he? Is this what we want? Oh, I also need to know apart from part E, that was yes, TL was the D should go to F of K. Hold on a second. I need this part E. How does TL act on FK? What modification of F of K corresponds? TL, I'm pretty sure. Well, let's do E first because I think we need the result from E. So E would be So TL of x goes to x minus L. So we have R1 over root 2 pi. Root 2 pi. Yeah, root 2 pi. Negative infinity, positive infinity. And now we want, which one do we want? Yeah, dx e to the minus I k x minus L f x minus L is equal to now this is going to be this is e to the I k L e to the minus I k x. This one won't matter, so this one is going to be e to the I k L f of k, right? This is e. So the derivative operator on f of k let me just see up here if we did IK x, and then we had plus no, I don't think that's helpful. Study account is asking, do I ever look up these notes again for revising? Do you mean like after this class is done? I'm not quite sure what you're asking. Oh. I think this is adding this e to the I k L to this. No, these are just rough work for solving. There's nothing really special about these. I mean, I'm sometimes looking back in the class to sort of see what I did in sections, so they're not useless as notes, but this isn't like some kind of study guide I'm going to go back to. Look, I do have textbooks and stuff. My goal is to try to get the knowledge here, not to worry too much about it here. I do have notes from the lectures, but this is just kind of scratch paper for solving problems. Yeah. EDIKLF. Okay, this is E, I think. Let's look at answer for E first, and then see if we got it right and move forward. E. Oh, minus, right? So we did get this part right. Yeah. Oh. Now let's try F. Okay, and then what do we want to do? We want to have D on F of K. What? Hmm. Hmm. Well, let's expand our. So we know that this was TL is equal to E to the minus LD. So let's just start by expanding this. I feel like it's IK this, right? Let me just try. I'm blanking pretty hard on this one here. Have to put it together. You know what? I don't really want to give up on this just quite yet, but I might need to take a little break in order to do it. I was going to work a little bit longer this morning, but I might just take my kind of morning break a bit earlier and get back to it for a little bit longer in the afternoon. So I think I'm going to just take a break right now because I don't really want to look at the solution for this, but I don't think I can solve it right now. So I will wait, try again with kind of fresh eyes in the afternoon. And if I still can't get it, then I'll have to just look at the answer. So yeah, I'll probably be back a bit earlier this afternoon. I'll just sort of see how much work I have to do. And then once I get done that, I can get back to working on this. So thanks for everyone who's been tuning in. I will be back probably in